Welcome, everybody. It is 1 minute past 2, and we hate to start these things late because then sometimes we might even finish late, and I know everybody's probably pretty busy and like to get this done. My name is Roger. We're going to talk today about generation of electricity from variable renewable sources and the effect that has on the grid. And let's just talk about a few procedural issues here. The chat box we're going to save for any administrative issues, like if you all of a sudden your sound goes out or video goes out or something like that. Use the chat box and type that in so the host will see that issue. And you can determine then, hopefully we'll determine whether it's local or overall. But the whole idea of this being a live webinar is for there to be exchange of information and ideas and questions, and that's what the Q&A box is for. So please make sure you found your Q&A, and if you have a question, type it in there. I'll be checking the Q&A box pretty regularly, and usually my computer screen flashes at me that, hey, wake up, you got a question, and we'll respond to that. The worst question is the one you don't ask because you're paying good money for this experience. And if you have questions or comments, they are most welcome. The worst answer you'll get would be, I don't know. And that's always a possibility. Or I might even say, I'm glad you asked that. We're going to be covering that in about 15 minutes. So don't be ashamed to type in a question. That's the way we fill in between the lines. The statements on the slides are the outline of the talk, but the essence of the talk is whatever exchange we might have. Okay, so here we go. First, need to give credit to the National Renewable Energy Labs. Back in 2012, they commissioned a renewable electricity futures study. The whole idea was to determine, I mean, as the title of this webinar indicates, variable renewable sources. We've got some measurable percentage now on the grid of renewables. But what happens if we got up to 80% and all this variability? I mean, predictably, the sun goes down every night. Well, unless you're up in above the Arctic Circle in certain times of the day or below the Antarctic Circle. But otherwise, the wind is a little bit unpredictable. If you're going to get a bunch of it, you probably know about that, but it dies off. So how do we deal with that? We're going to be talking about that. And we also, since this is a 2012 study that we're hoping for, maybe they would be able to verify what it would take to provide 80% of the electricity to the grid by 2050 from renewables. It's now 10 years after that study. So we're going to look at additional information as to where we've come since that study was commissioned and see where we might even be able to do a whole lot better than they were hoping for. So REFS stands for Renewable Energy Futures Study. And if we have other references, I've made an effort to document them with information on a particular slide. So if you want to use this material, don't worry about copyrights on it and help yourself. You're welcome to download the slides at the end of the session for your own use, whatever use you might like to put them to. Okay, so with that as background, here we go. What are we going to do? We're going to, well, that was the introduction. We've done with that already. How about that? Moving right along. We're going to talk about photovoltaic systems, wind systems, and the effect these systems have on the grid. And then what are we going to do about it? And what can we do about it? Is it going to be too expensive? Is it just pipe dreams, or is it reality? Have some of these things, are they already available? So starting with photovoltaics, it is not just a hobby anymore. This picture, by the way, is a 10,000 watt battery backup system installed about 10 years ago. Florida installed about 120 of these at a number of schools around the state to use as hurricane shelters. So here's some, in 2020, 3.1 gigawatts of residential PV systems were installed in the United States. In 2020, 16.57 gigawatts total PV was installed in the United States. So you can see that residential is a small fraction of the total, about 20%. And commercial and utility scale are the other 80%. In 2020, around the globe, the added PV capacity, that's the capacity that was added in just that year, 2020, during the pandemic, was 107 gigawatts. And in 2020, China installed 48.2 of those 107, and India installed 3.2. So when people say, what's the point in the United States getting involved in this? Nobody else is. Well, they just haven't read the newspapers because, in fact, the matter is China's way ahead of us. And jobs, yeah, 317,000 solar jobs in 2020. I happen to be in one of them. So that only leaves 316,999 other folks along with me. And PV efficiencies continue to improve. The reliability of solar continues to improve. And the prices keep coming down. They've kind of leveled off now for the last year or so. But compared with other prices that keep going up, leveling off is not half bad. So let's take a look about some of these numbers here. If we just look at the cost of the solar modules themselves, those things that you stick out there to capture the sun. Back in 1976, they were over $100 or 75. They were over $100 a watt. And in 2015, they were down to around, if you can read that logarithmic scale, around 80 cents a watt. And if you move just a little further out in 2020, they were about 30 cents a watt. So, and in 2021 and 2022, they're right in this neighborhood around 30 cents a watt, which isn't half bad given the inflation that other things have experienced. Okay, so if they're this cheap, then how much does it cost? That's one measure. And of course, they last, most are now warranted for 30 years to have at least 85% of their initial power output 35 years later. That's not too bad, kind of an attractive feature. And so let's look at a few numbers here more. Are people buying them? Well, matter of fact, yeah, they have been buying them. And in fact, as you can see here, it's increasing. If that were a straight line fit there, we're looking at exponential increase since the vertical axis is logarithmic here. And so if we try to predict the future, where are we now in 2021? Well, we're right between the green line, which would have been the maximum, and the blue line, which would have been the worst case, the lowest. So trying to project from around 2007 where they might be going. So, and if we just look at the cost, if you want to install residential, it's going to cost you around $3 a watt for a straight grid connect. That makes kilowatt hours for you with no storage. That's before the federal investment tax credit of 26%. If you and so that knocks your price down by 26% because that's a direct tax credit for you. And utility cost in 2021 for an installation is about $1 a watt. So that's pretty. That is incredible because I can remember I've been around for a little while, and back in year 2000, it was thought that just the glass and the frame of the modules would limit the price of solar. It looked like the glass in the frame was going to cost $1 a watt. And now we're down to 30 cents a watt. So guess who was wrong? And this is in 2020 dollars also, not in 1975 dollars. So that makes this whole picture look even more attractive. I see a hand raised in the Q&A. Let's go up there and see what we got. Please tell me where we can get solar panels for 30 cents a watt. We're seeing double that as prices have been crazy in 2022. I can't tell you where you can buy them for $30. Well, I can tell you that you can get used ones for 30 cents a watt from Sun Electronics down in Miami. And maybe they are higher at this point. Some of them are higher. Down here in Florida, when we buy the modules that need to resist 175 mile an hour wind, they are a little stronger frame and all, and I think they're a little more expensive. All I'm telling you is this is what you get if you ask the United States, let's see, Energy Information Agency, the guys who do the statistics, and they are showing somewhere around 30 cents a watt. Maybe they're up at 60. Not sure, but even that, let's look at, if you talk about the system installation cost of $3 a watt, we are still seeing that down here. Okay, and I thank you for your question. And 30 cents a watt, not all these numbers are necessarily exactly right. It depends where you find it. I thought I had a reliable source, and if you can't find that price, and it could be what we're talking about is if you want to buy 100 megawatts for a utility scale plant, you can probably buy them for about 30 cents a watt. But if you're buying locally, I doubt they're going to sell you that kind of a quantity for, 10 kW or 100 kW for 30 cents a watt. No, probably not true. Okay, but thanks. I appreciate you pointing that out. Regardless of the price, they are still selling like hotcakes. My job is to review sets of plans before they're sent to the contractor for going off the permitting. And in the last year and a half, we have reviewed more than and produced more than 31 megawatts, or which is roughly 3,100 sets of plans for residential installation. So they are selling like hotcakes down here in Florida, and I know that that's also the case elsewhere, especially where there are incentives. And we don't have any other than the federal. Let's look at where we might be headed. This is important as far as energy storage, as far as whether or not we can achieve 80% by renewables by 2050. What we're looking at is the lines up on top are the three conventional fossil sources. We've got on top is oil, then coal, then natural gas. And you'll notice that natural gas has been moving up here a bit since 2015. And oil has bounced a little bit around. 2019, 2020 went down a bit when people weren't driving as much. The question is, where are we going from here? Notice the blue and the green. They are kind of important. The blue, that's nuclear. And what's interesting about nuclear is nuclear has kind of leveled off, and actually back in 2019 worldwide, renewables outpaced nuclear in terms of the number of kilowatt hours that they produce worldwide. So renewables are in the game for good here. Question is, will they continue growing exponentially? And if so, when will they hit the level that the fossil fuels are generating? Because unless we do an awful lot of conservation, we're going to want at least as much energy in 2035 and 2040, and particularly if we adopt to electric vehicles. So there will be a great need for electricity. The question is, how's it going to be made? And these are some possible scenarios. It is possible that by 2035 or so, if you start adding them all up, coal is starting to go down. Oil might go down if, I mean, I see a lot of Teslas and other electric vehicles driving around my neighborhood. So anyway, it's a guessing game, but if in fact projections are worth anything, it's certainly a possibility if we get enough people employed that we'll maybe be able to surpass the fossils by as early as 2030. And it's just on not known. I'm hoping I hang around until 2030 and see what the story is then, because it's getting pretty exciting right now. So just some numbers here, and this is you know, we hear a lot of bad news, but maybe what we're seeing here is some optimistic news, and maybe it's too optimistic. We're going to find out. Okay, so this is probably the worst, awful busy slide you've ever seen in your life, but I want to show it anyway. And the reason is because this is, NREL has been, the National Renewable Energy Labs, you can see that in the upper right-hand side. They've been tracking the progress of various technologies. And if you look at something like perovskite, that's the little, kind of the lower right-hand side, where you see the red circles with the yellow insides, and it wasn't even on the map until 2013. And in 2017, it was up at 22% efficiency. Why isn't it replacing silicon? Well, they haven't stabilized it sufficiently well at this point. But point is, what we have to use in 2030 might be a whole lot different than what we have to use in 2022 and 2040, 2050, whatever, in terms of materials. And that doesn't just hold for the solar itself, it holds for batteries and everything else, because people are onto this. There's money to be made. And when there's money to be made, people respond and they invest and things happen. So the idea is, stay tuned. There's some interesting stuff out there in the laboratories, and at some point, it's highly likely some of that's going to show up on the rooftops, in the backyards, and out in the big solar farms. Okay, a little information on the sun. And by the way, let me tell you right now, we're going to talk about some large storage systems as an obvious way of meeting the times that the clouds come over the sun, and when it's dark outside and when the wind stops blowing. But I don't expect anybody to leave this webinar being able to go out and bid on a 100 megawatt hour energy storage system. But you'll probably find out that they are out there, and at least you will pick up on some things that maybe haven't been obvious because you've maybe been too busy to think about them. Okay, so let's talk about sun for a minute. Peak intensity of the sun is about 1,000 watts per square meter. So that's as much as you're going to get, even no matter how hot it is, because if we don't re-radiate that energy that comes in, then obviously the planet has to get hotter. That's the second law of thermodynamics. Peak intensity is 1,000 watts per square meter. So therefore, anybody who tells you that they can make 2,000 watts with the one square meter worth of solar, maybe that's concentrating, but it's going to take 2 square meters worth of sun focusing down on that 1 square meter of solar if they want to make that 2,000 watts, because 1,000 watts per square meter is what you get with the sun directly overhead at sea level. And if the sun comes in at an angle, goes through more atmosphere, then the intensity goes down. Okay, so depending on technology, you see that busy curve there not long ago, but about 22% can be converted to electricity. And this means cost effectively with relatively low tech. Most of the modules that we are using now in our design work are roughly 20% efficient. So that is every square meter of your roof, you should be able to generate a maximum of 200 watts per square meter, and probably going to be less just because of other reasons. But still, added up over the year, it's a significant amount of electricity depending how much. You deploy, the typical house with 10,000 watts of solar will make almost 100% of their annual electricity requirements if they've got energy efficiency and other things involved in the construction of that house. Conversion, and this is what really counts, is normally between 1,000 and 2,200 kilowatt hours per kilowatt per year. Depends where the system is. It's very much depends on the location, but also the orientation of the system. If the modules are facing north, you're going to lose about 30%, depending exactly where you are. But if they're facing directly south, a reasonable number to use. If they're facing south at latitude, they will probably average around 1,500 kilowatt hours per square meter per day. Now, of course, you don't have to use that guess because there are lots of sophisticated performance models out there. And one in particular that is totally, it's no cost because it's paid for with taxpayer money, is the System Advisory Model, SAM, from the National Renewable Energy Labs. And all you have to do is Google National Renewable Energy Labs and look for SAM, System Advisory Model, and you can download a free copy for yourself. It's very intuitive, and you can get the exact number for your particular house orientation and so forth. What's significant is that the energy out of a module is proportional to the sunlight intensity on the module. And that's how it boils down on solar. But now solar is not the only player in this game. Wind is also out there. What about wind? Where are we headed? What's happening? Well, in 2022, if we go to the United States Bureau of Labor Statistics, they will tell you there are 85,000 wind industry jobs in the United States. That's actually fewer than there were in 2016. But I think that probably the wind industry was hit pretty hard by COVID. We'll see what happens in the next year or two, because the numbers are very promising in terms of the recent 2021, 2022 installations. In 2021, worldwide installations added up to 97.5 gigawatts. And that's just what was installed in 2021. The cumulative total as of 2021 worldwide for wind power was 840 gigawatts. Now, this is not gigawatt hours, this is gigawatts. All right, so the question is, how many kilowatt hours can you make, or how many gigawatt hours can you make in a year's time with that much wind? Well, it depends where it is, once again. And one thing about wind is any mechanical engineer would be happy to tell you that the force of the wind is proportional to the square of the velocity of the wind. And if you want, that's force, but if you want power, then you have to have force times velocity. And the velocity on these is the rotational velocity of the blades on the wind machine. So you have to convert a linear velocity into rotational velocity. There's some losses there. So you're looking like almost the cube of the velocity then as being a factor. So therefore, that's why they say if you don't have 18-mile-an-hour sustainable winds, then you're not a very good wind power site. And ask any of the folks who are installing wind, and believe me, all the big wind installers are all looking for where the wind blows. and they are planting windmills. So in addition to 2021, and this is a number I searched and searched and searched on Sunday to see what the story is on small wind turbines in 2021, and the best I could do was the situation in 2014, that they have a total capacity of 830 megawatts, and there were 945,000 of them then. It's reasonable to believe there must be over 1 million at this point. And here's the thing, the large wind turbines in the proper location is going to give you close to 2,300 kilowatt hours per kilowatt per year, as opposed to the 1,500 average for solar. The only thing is the 1,500 average for solar is pretty much average for everywhere, whereas the 2,300 is what the people who make electricity for the wind look for. And that's about equivalent to planting PV modules on tracking collectors in the desert, and then they can make that many. It's all a matter of dollars and cents. What's your overall investment? And so we'll take a look there. But again, the construction costs for windmills reported by the energy journals and the government energy agencies is in the neighborhood of $1.50 to $2 a watt. And again, we talked about sustained winds. Imagine being the ball bearings in one of these rotors and having to deal with gusty wind. Not very good for them. They're not happy with that. So they're looking for a sustained wind. Here's a curve on a linear scale, but it looks kind of exponential, doesn't it, in terms of worldwide growth in wind power. And of course, you saw the picture of wind on that previous slide as well. Where's the wind? Our friends in China again, of course. Who else? United States is second with less than half of what China is doing in wind. Germany probably going like crazy to add more windmills wherever they can now to try to offset their dependence on gas from the east. But India, Spain, and Italy, and France, and Brazil, and Canada, they're all installing their wind machines. But again, I've mentioned this, that you simply can't cost effectively install wind everywhere. You are a little more limited in where you can install it. If you want this information, it's in the Wikipedia. Okay, now another evaluation measure is the levelized cost of energy, LCOE. And what this does is it takes into account what would you have to charge in cents per kilowatt hour or dollars per megawatt hour for your electricity in order to pay for the cost, maintenance, fuel, and the total cost of your system over the lifetime of the system, including decommissioning costs. And these are the numbers you get from the various people who track these things. And again, I have to tell you, these depend on the utilization factor, whether this natural gas plant is going to run 100% of the time, 80% of the time, 50% of the time. So the number that the folks who do these analysis come up with is 7.1 cents per kilowatt hour. For advanced nuclear, they come up with 9 cents. For onshore wind, 4 cents. Photovoltaics, 4.3, and that's an average. Less expensive for utility scale and more expensive if it's up on your roof. But still, it's the LCOE of PV on a roof here in Florida and most other places is roughly half what the local utility rate is, which is the convincing argument. Anybody who plans on staying in their dwelling for any amount of time, 10 years, it's very convincing to them to install a solar system. So, and my point here is not to sell solar. My point here is that it's happening, and here are some of the reasons. And hydro is at 4 cents. That's relatively inexpensive, but then there's the issue of time to build a hydro plant, and all the permitting, and all the land use, and all of the headaches involved in all the impact studies and so forth. But if, and finding a site, we don't have a whole lot of hydro down here in Florida. Anyway, this is from the International Energy Agency in 2020. And so go read their story, and they'll give you what all the assumptions they use. So, okay. What we see is variable renewable energy is on the rise. What's it going to do to the grid? All right. And of course, what we wanted to do, the whole goal of the grid is to give you and me our electricity when we want it, as much as we want. So if my water heater with its, I guess my water heater element is 3,500 watts about, and if it wants that 3,500 watts right now, it wants it now. It doesn't even want to wait a half a second for somebody to allow it to have that electricity. It wants it now. So that's what the grid is supposed to do, and that is no small challenge. Base load, essentially the minimum expected daily load. The total load is base load plus the variable load. And we're just running through some definitions here, and most of them you already know. Some loads very slowly and others very quickly. All right, and again, stating the obvious. One thing that is interesting, and electrical engineers in the group are presumably well aware of this, is that the more loads that are connected, you have a diversification factor that shows that they're not all going to be on at the same time, but my neighbor might turn on their stove just after I turn mine off, so that it is a stabilizing and a steadying effect. The more people out there and the more loads there are out there that want to use electricity. And of course, that varies from time zone to time zone, and that's another interesting leveling effect. So just as loads change their output, some very slowly and others fast, some sources can change their output very quickly and others are very slow to respond. Case in point, nuclear plant, typically a big one, may take 1 to 2 days to crank it up to full speed sufficiently carefully to make sure that it doesn't want to exceed its rated full speed. Pulling those graphite rods out, you got to do it pretty carefully. On the other hand, if you've got a flywheel, it can flip on in less than a second to make up for any kind of a utility momentary glitch in the system. And inverters in solar systems can turn on in a matter of milliseconds, very quickly. So again, some are fast, some are slow. So clearly the generation mix has to have some quick starting equipment simply to be able to fill in the gaps that will exist depending on the way the demand curve might look. And one thing that has been shown is that distributed renewables can possibly affect substation equipment. So in other words, if you have a lot of solar, you'll generally do a grid impact study if you want to do a large system, 10 megawatts or bigger, sometimes smaller than that. And the utilities want to know if you're going to be sending electricity back to the substation, if the taps on their transformers are going to be moving back and forth rapidly and burning out before they're supposed to. So that's a concern, and studies show there is a limit to what can be done to make sure that doesn't happen. On the other hand, if it does happen and you've got electronic switches rather than mechanical switches, which I'm sure will be probably coming on the market fairly soon, then that problem will probably be solved. So looking at the grid, it is no simple network of wires. It's a system of systems, in fact, starting with fuel and other resources, lots of different methods of generation. Once you generate it, you got to move it to the user with transmission and distribution. And of course, load. If there were no loads, there would be no purpose of generating the electricity in the first place. And if you're going to generate this stuff, you have to kind of keep track of what you're doing, because once you see that you are overdoing it or close to reaching a peak in one plant, you're going to have to turn something else on. So you need to have a network and a way to measure this. You need information control systems. They are becoming more and more sophisticated all the time. To the extent that the utility can now, by way of IEEE 1547-2000, utility can sign an agreement with a small generator that the utility can actually control the amount of power being generated and added to the grid, as well as the power factor to help stabilize. So there's some really interesting information and control. And what's behind it all? Money, of course. And let's don't forget the regulators. My goodness, where would we be without them? So all parts of the grid. Fortunately, I don't have any more room on the slide, or there might even be more to the grid, but this pretty much summarizes the major parts. So if you want to do things with the grid, it's nice to have a model for the grid. And to begin with, it needs real and reactive power. Reactive power is simply, if you turn on a motor, there are lots of magnetic fields in that motor, and those magnetic fields don't use energy themselves. They transfer the energy from the stator to the rotor, and in the process, that energy transfer is transferred out of phase. The current is out of phase with the voltage, and so when current times voltage does not equal the power that you would measure with a watt meter, it means you've got some reactive power involved. And it means that way current times voltage would be greater than what you would measure with a watt meter. So, but the grid needs reactive power, and preferably it needs some reactive power that will offset the reactive power that's being used by the loads. Oops, went the wrong direction. So it's nice if the generation sources can do both. And mechanical engineers know about mass spring dashpot systems, electricals know about RLC circuits. The idea that you can lead to instability is if you have fast changes where you have all of these components in a system. Now, R is mostly what the load is, and the more resistance you have in the system, the more damping you have, and it's less likely the system's going to go unstable. So the modeling of the grid likes to model the amount of load, the amount of resistive load, as a measure of the stability of the grid. Because if it bounces around and the measuring instruments notice that, they might decide that it's necessary to shut down a generation source to protect it. And usually sources ramp on and ramp off. They don't just instantaneously turn on and instantaneously turn off, although some can. But even using a ramp as a stimulus, and you talk about stimulus response problems, ramping itself, if it ramps too fast, it can actually cause some instability. It depends on what's out there. So in order to determine what's out there, it's good to have a model of the grid. And there's some very complex software available now to do this kind of simulation. So, and it's like looking at looking at the response of an RLC circuit to an input ramp function for the electrical engineers. For everybody else who that doesn't mean anything, don't worry about it. Okay. In any case, if you ramp too fast, it could be unstable. You need to watch that. And in fact, that also holds true then for your solar and your wind. You need to be able to sometimes slow down the rate of it coming on or off. Sometimes it's good if it ramps up quickly, because if you lose a source, you want to replace it as quickly as possible. Otherwise, you have some real problems. Here's a question. Let's take a look. What are some of the names of the software package available for modeling grid fluctuations? You know what? I don't know the name. I have a study here, but it would take me too long to find it. I'm going to give you a name of a company that uses this software. I think it's RC Engineers in Orlando. There's so much software out there, folks. I'm sorry, I can't keep up with it all. And this is the first time anybody asked me for the name of it. I've seen the results of it. What I've seen is, in fact, it's a garbage in, garbage out, as for any software. This particular modeling, they said the solar system is too big because the minimum load, it exceeds the minimum load. But what they forgot about is the minimum load was at 7 in the morning when there's nothing coming out of the solar system. So I guess maybe my answer is watch out for the software packages. Make sure you understand what their limitations are. But I'm sorry that I can't give you the answer. I bet you could Google something though. Software for modeling grid fluctuations, and so I'm sure something would come up. Okay, let's see. But it does exist, and I'm sure that a Google search in a matter of 5 minutes would find it faster than I could almost look it up for you. So let's look at some results of grid modeling. You need to smooth out rapid changes. Okay, well, that's pretty predictable. One thing that's less obvious, though, is that generators are not designed to absorb power. And I put that in big, funny looking type because it's an important thing. If you have way too much renewable power on your grid and it has no load, it's going to seek out wherever it can go, and it will try to make your poor fossil generator run backwards. And fossil generators, the prime movers, are not at all happy about being asked to run backwards, because if you run that current into the generator backwards, then it acts like a motor. So what fun that is when you got a thermal source trying to rotate that thing in one direction, you got solar source trying to make it move in the other direction. So there's some interesting switching that needs to take place. And of course, folks who do these things, they know about this, but we all need to know that too. That's why these people earn such good salaries, because they know about this stuff. In any case, if wind or generation, if it tries to feed the power to it, it's not happy. Okay, and so you have to do something about it. And there are ways of doing things about it. And mostly what it is, you got two choices. You take the fossil generation source offline, or you back off on the other source, or you switch in something that will use that renewable energy and save it for another time, which means the implication here being using storage. So in 2012, NREL did a comprehensive study of these concerns, and here's what they found out. They found out that renewable, I'm going to read this. I don't normally like to read my slides, but just let's read it together. The central conclusion of all the analysis is that renewable electricity generation from technologies that are commercially available today in 2012, in combination with the more flexible electric system is more than adequate to supply 80% of the total United States electricity generation in 2050, while meeting electricity demand on an hourly basis in every region of the United States. There's our bottom line, okay? Yeah, it's possible. And that's what the study concluded in 2012, and nobody has proved them wrong at this point. In fact, if anything, it looks more like it would be possible to supply close to 100% of the total electricity generation with renewables by 2050. And that means there's going to have to be some means of storage, clearly, and ways of leveling. So we're going to look at some of those as well. And as far as the 2012 study is concerned, if there's 80% renewables, that's 20% of other stuff. And who knows exactly what that might be. Clean coal. They're still working on that, I guess. So what could be some contributions or contributors for achieving these 80%? Well, one is more flexible conventional generation. Probably not going to have a 500 megawatt nuclear plant that you can turn on in 15 minutes, but there is other conventional generation that can be made more conventional, more flexible. And inverters, I think, are going to be playing a large role in this, because an electronic inverter using power electronics, which is what's used, of course, when you have a DC transmission line, you have to convert to AC at the other end. And very typically that's done electronically. I mean, it could be done with DC power generators, but it can also be done electronically. And but now the need has been identified, so you can bet that people are working on it. Storage, an obvious thing. Save energy when you don't need it for when you need it. New transmission, probably will need some more transmission, maybe some more DC transmission line. And even the loads themselves, maybe they can be made a little bit more responsive. Maybe the loads, I mean, my goodness, my neighbor's got smart everything. He's got smart refrigerator, smart washing machine, this, that, everything is smart these days. And so that smart thing could be communicating with the grid and saying, hey, in 2 minutes, my element's going to need more electricity, so get ready. Who knows what's going to happen? It gives somebody something to do, that's for sure, to figure it out. And just changes in the way we operate power systems, scheduling and so forth. We'll see that a little more as we move on. And more robust substation taps, as I had mentioned earlier, to take care of the concern of renewables going back through a substation and causing the transformer taps to fail prematurely. And so if you do all that, what can you get? Well, big reduction in generation cost, big reduction in water use, something a lot of people don't think about, but utility scale solar uses about 1.3 fluid ounces per kilowatt hour generated. And that's not even in Florida, because what this 1.3 fluid ounces is for keeping them clean. And any place where it rains, you don't need that. If you've got a natural gas turbine, they use about 25 fluid ounces for cooling for every kilowatt hour generated. That's quite a bit more, isn't it? That's almost 20 times as much. So water. And well, there's a whole lot of people around the country who have got a whole lot more water than they wanted to have recently, but then there's a whole lot more places where the fires are burning and they don't have enough water. So maybe not having to use it for generation of electricity could put it to use elsewhere. Then, of course, significant reductions in electric sector greenhouse gas emissions, but not only just greenhouse gases, but also all the nitrogen oxides, the sulfur oxides, and the particulates. So breathe easier, everybody. all that stuff that affects breathing. If we can reduce that, maybe the allergists will have to become podiatrists or something like that, because people will be out running and exercising in all that fresh air. But there are all these transitions that do tend to happen. They've happened when the horse and buggy transitioned to the horseless carriage, I guess. So the idea that solar and wind have no greenhouse gas emissions from fuel, the only greenhouse gas involved is construction and decommissioning, and every energy source has construction and decommissioning, and mining for that matter. So we can't, that fuel use, it makes a big difference, or not use. Okay, so whose job is it? And let's take a look. Most of the puzzle pieces are in place for optimizing grid performance. It's the North American Electric Reliability Corporation balancing, Okay, you can read this slide because we're going to take a look at what these various entities are. So there's no need to dwell on them at the moment. And in addition to the regulatory folks whose daily job it is to make the electricity as efficiently as possible, there's the regulatory agencies out there at federal, state, and local levels who also are the watchdogs to make sure that these other guys are doing their jobs. So let's take a look at the North American Electric Reliability Corporation. What do these guys do? And there's probably some women there too. I don't mean guys, I'm using as a general term. I'm not trying to, there's plenty of women involved. Well, here's the interconnections for NERC, and you can see down there at the bottom is one of the big problems that we've had here recently. Poor Texas is off by itself. And if it gets really, really freezing cold down there, they've discovered they have a problem. If it gets awfully, awfully hot down there, they can't borrow any electricity from any place other than themselves. And I'm guessing this map will change. I'm guessing the folks in Texas will do a little negotiating with the Western people and with the Southern people. Now, all these acronyms here, we've got some definitions for them. So if you order the slide, you'll find out what all these folks are. You notice that Florida, the FRCC and the SERC and the RFCC, all these others, they're grouped and they work together and they share electricity across lines. And notice that it's not just limited to the United States. You can see that part of the Midwest group includes Alberta and Manitoba. So, wait a minute. Saskatchewan and Manitoba, my mistake. Canadians in the audience, forgive me. We did visit Canada for a little while this summer. Okay, anyway, the Federal Energy Regulatory Commission, FERC, well-known group to the regulators and utilities around, they regulate the interstate sale of electricity. So the North American Electric Reliability, the NERC, has the authority under FERC for the reliability operating and standards. And under them are balancing authorities, regional entities, utilities and power pools, and transmission organizations. So we're going to take a look at those now. What are balancing authorities? Well, they're responsible for balancing between load and generation. So therefore, they have to anticipate what the load is going to be and make sure there's generation available. They're responsible for maintaining frequency, because if you lose frequency, that's a trigger to tell generators to turn off. Sometimes you don't want to do that. So therefore, they maintain ties to adjacent balancing authorities so they can talk to each other about who needs what when. And when they reach these conclusions, like it's going to be really hot tomorrow, they start getting ready today to meet that demand tomorrow by cranking out every last kilowatt hour or kilowatt worth of generation they have in order to meet their anticipated demand. Okay, so if that means they can import or export to the adjacent balancing authorities in order to, the whole idea is to buy the cheap electricity from the least expensive and most reliable source if they have it available. That's called optimizing performance. And one way you have to do, one thing you for sure have to do is you have to schedule your generation to make sure you minimize the generation costs. It is necessary to have some spinning reserves where you actually are fueling up these fossil fuel generators, but you are not connecting them to the grid to make electricity, but you have them up to speed at either their 1800 or 3600 RPMs, most likely probably 12 or 1800, in order to be able to relatively quickly synchronize with the grid frequency and add to the demand during the day. And that's the job of the balancing authorities to make sure these folks are ready to go. Then there's the regional entities, and they're shown on the NERC map. And these are, it's so much fun too. I mean, for one thing, you at dinner tonight, you can talk about, we learned about NERC and WEC and TREE and MURO and I learned a whole bunch of new acronyms today. And most of these, you know, I'm not going to encourage you to memorize them, but if you download the slides, then you can look at them and if you want to figure out what MRO means. All right, anyway, what therefore they are responsible for improving the reliability of the bulk power system. And these entities, see, there are some regions where the grid fluctuates more rapidly than other regions. Out west, it's not so bad, but up in the Northeast, the fluctuations are more difficult to anticipate. So therefore, their planning is more complicated. And so all segments of the electric industry are members of the regional entities. And they account for all the electricity in the United States, Canada, and part of the Baja California norte of Mexico. So between 1935, you know, what about utilities and power pools? Well, in 1935, the Federal Power Act came on. 1992, the Energy Policy Act came on. 1935, the idea was these poor farmers, they're growing food for us. We need to get some electricity out there. And the whole idea is to design for reliable electricity at minimum cost to everybody. And they're regulated to make sure that all the rates are just and reasonable. And they are members of the utilities and power pools are the investor-owned utilities, the munis, the co-ops, and the federal and state generators, Bonneville Power Administration, Tennessee Valley Authority, and so forth, federal generators, and they are members of these local groups. Power pools in Pennsylvania, New York, New Jersey, and New England were organized to cut costs through power exchanges across the regional networks. That was done a while ago as a result of the these two acts. So what about the regulatory constraints of utility system planning? I haven't seen a question for a while. Have I put everybody to sleep? Or are you disappointed with the fact that every time you ask a question, I say, gee, I don't know. Well, that's right, you don't need to comment on that, but I hope we are not putting folks to sleep unless, here's, okay, let's see what we got here. Oh, John, thank you. I'm glad you're still there. Okay, great. Okay, utility system planning, regulatory constraints. What might they be? Whoever heard of regulatory constraints? Well, before 1990, the investor-owned utilities pretty much ran the show. Planning to do, hey, you want some more generation, want another transmission line? That's okay, we'll handle it. We do the generation, we do the transmission, we do the distribution, and you know, we send you the bill. But then along came the Energy Policy Act of 1992, and it said, hey, guess what? If there's somebody out there who wants to make electricity, case in point, the sugar mills in Florida, after they've made their sugar, they have all this leftover sugar plants called bagasse. And they burn that stuff, and they wanted to be able to generate electricity with it, because why just put smoke into the air? Why not make some electricity? Well, that's seasonal, and utilities weren't particularly happy about it, but the Energy Policy Act said, guys, sit down at the table, negotiate a price. You have to buy the electricity as long as it is grid worthy, meaning it has to be nice sine waves, proper frequency amp, and properly voltage and stuff like that. Okay, another example in Florida was the phosphate mines. Mining phosphate needs sulfuric acid. To make sulfuric acid, you burn sulfur. That's exothermic. The folks making their sulfuric acid wanted to use that excess heat to make electricity. Well, that's not quite as seasonal. And again, the EPA of 1992 said, you guys got to sit down and you have to agree on a price. I remember that well, because I sat down with representatives of both of them, and we talked about how you need to do this, because the Florida legislature is adopting the rules here so they can get some federal money. So let's be open-minded here and see what we can do to make everybody happy. And what fun that is. So the regulatory implementation of this actually began with two FERC orders, Federal Energy Regulatory Commission, number 888 and number 889. That happened in 1996. And Rule 888, what that did was it unbundled transmission services from sale or marketing of electricity. Gee whiz, transmission services. That means that you can build your own transmission line as long as you can find somebody who wants to put electricity on it. The ARRA of the American Resource, that's the Recovery Act of 2009. The Department of Energy initiated coordinated interconnection-wide transmission planning as part of the ARRA back in 2009. So there are certain regulatory things that have happened. Here's a Q&A. Let's see what we got. Oh, Jennifer. And that was at 3:01. Made it for a whole hour. In the afternoon, that's great. Thank you very much for your response. Much appreciated. That means we actually have 2 out of 37 people who have confirmed that they're still there. Okay, so there's lots of rules that have been passed to say, okay, we need a little more flexibility here. If somebody thinks they can build a better mousetrap, as long as they can, that mousetrap, whatever it might be, transmission line, distribution line, whoever, as long as it's something that does not mess up what's going on already in the system, then go for it. In 2011, there was an order that was intended to foster greater cooperation in generation and transmission planning. Oh my goodness. Ordered to do that when it makes such good sense anyway. But now you kind of have to do it because they told you you have to do it. Gee, another Q&A. Let's see what we got. Oh, there's Don. Thanks, Don. Okay. Then there's other organizations out there called transmission organizations, the ISOs. And open access to transmission systems mandated by 1992 Energy Policy Act. So you need system operators to take care of that. Okay. And there's the regional transmission organizations, again, part of the FERC Order 2000. It says you have to have non-discriminatory access to transmission. Anybody who wants to upload electricity to your transmission line has to be allowed to do it, provided that it is good electricity, that it will not mess up your system, and so on. So fine, you do a study, you do a simulation, and you prove that, okay, you can handle so many megawatts at certain times of the day, whatever, and you do it. Another Q&A. Okay, yep. Thanks, Sheldon. I think I started something here. Okay, no need to tell me you're awake anymore. Otherwise, I'm going to spend the whole time looking to see whether it's a question about what we're talking about. Okay, so we got independent system operators and we got regional transmission organizations. Okay, and we've got, what else do we have? We got regional transmission organizations. And it basically, that's what utilities from one or more states, they try to incorporate the regional transmission organizations into their planning and marketing. So traditional utilities are not necessarily all in RTOs, but generally they do have regional planning. It's generally to their own good. And merchant transmission organizations that plan transmission projects and seek funding for them, there are groups like that as well. So transmission is an important part of getting electricity where it's needed, when it's needed. Here's a map of the independent system operators. Again, we'll not spend a lot of time looking at this, just if you want to know who these folks are. And notice they're not everywhere. Wyoming doesn't have one, Colorado doesn't, Utah doesn't, Nevada doesn't, Idaho doesn't, so on, not even Florida. So the regional transmission organizations are not necessarily everywhere. So how do we keep the grid reliable? First, we have to define it. And what it means is meeting customer end use needs, even with reduced system availability. You need it adequate and secure. So let's see what that really means. Adequacy is defined as the ability of an electric system to supply the aggregate electrical demand and energy requirements of the end use customers at all times. Here's the important part: taking into account scheduled and reasonably unexpected outages. Key word there, unexpected outages. Expect the unexpected is the rule behind adequacy. So you can't get by with it saying we didn't expect that. You got to expect the unexpected, otherwise you don't have an adequate system. That's got to be fun. I'm kind of glad that's not my job. Security, what's that defined as? The ability of an electric system to withstand sudden disturbances such as electric short circuits or unanticipated loss of power systems elements. Aha. Now that's a whole lot bigger deal than an unexpected outage. I mean, yeah, that's kind of an unexpected outage, but if the system is able to withstand these kinds of disturbances, then the system is considered to be more secure. What about stability? Well, that's the ability of an electric power system to maintain equilibrium between generation and demand during normal or abnormal conditions or disturbances. All right, it's not good enough just to have everything work when everything is terrific. You got to take into account that there's going to be problems out there, And even if there's problems out there, you are expected to maintain electricity. So get on out there and trim those trees, whatever you have to do to make sure that you are as stable as possible. Now, there are ways of quantifying this, and we'll take a look at those in a minute. System planning operation requires all areas of interconnection to operate within specified voltage and frequency limits. You take an area and say, this is it, voltage has to be, whether you're at the distribution level, 12,800 plus or minus a certain number of volts, whatever. But planning requires that, and you have to do what it takes to make that happen. And frequency is just as important as voltage. After all, if you got an old clock that runs on a motor, it could be a minute or two off by the end of the day if your frequency of the utility were to slow down too much or to speed up. And generation transmission equipment has to operate within normal limits. So that's important too, normal limits. What's the definition there? But anyway, people know what the answers are, and we're simply defining what grid stability is all about. So part of grid stability means planning your reserves. And in other words, how much reserve margin do you need? Do you need to be able to crank on 20% more electricity within a half an hour because you know that pretty soon you're really going to need more? One nice thing about fossil generators is they can be running and they will supply a load pretty much up to their rated load. Think about your 5 kW generator that you've got outside in case you have an ice storm or a windstorm or whatever. That 5 kW generator doesn't put out 5 kW all the time. It'll light a 100-watt light bulb for you, but it might use almost, say, half as much fuel as it would if it's going to light or heat up a 4,500-watt water heater. So in other words, the efficiency it goes way down on a fossil generator when it's not putting out its rated load. But you got to have these things going. You got to have something out there to preserve that reserve margin. Now, what's interesting is I did one of my continuing ed courses just last weekend and learned about flywheels. And most of those disturbances on utilities are less than a couple minutes long when they're switching power or another power generation kicks in and you have a little bouncing around of electricity. So stabilizing that is important. And one way of doing that is with flywheels. We'll come to that. Anyway, a definition of planning reserves additional capacity above and beyond the expected peak so that sufficient resources are available at all times to meet the peak demand. So you got these fossil generators running, not adding any power to the grid, but waiting for the call to tie in because we need you now. Some of these may only have a demand factor of, say, 5%. I don't mean demand factor, utilization factor. They're there, but they're only used 5% of the time. And if you have to pay for your generator based on something that's only used 5% of the time rather than 90% of the time, you have to charge a whole lot more for the electricity. Here's a question. Let's see what we got. I'm wondering about the age and condition of our grid infrastructure and climate change. How have these impacted the security and stability of the grid system? Well, I mean, aging has always been that's called entropy. Presumably, utilities are continually trying to keep up the grid and keep it improved. And the question is the ability of the electric grid to be hacked being addressed as a security concern? Hey, you know, if I knew the answer to that, then it wouldn't be very secure. But all kidding aside, we're going to be looking a little more at what needs to be done to make sure that the grid is available. And we're looking at some of the people who will be responsible for doing that. So as far as climate change is concerned, that's what this is all about, is trying to adapt to it and trying to prevent it from going off wild. We are dangerously close to reaching a level of instability equivalent to a meltdown with a nuclear reactor from not being able to stop the warming. And so it's essential that the utilities are working on the grid system. And as far as being hacked, you can betcha they're working on it. And I have no idea exactly what's being done. And I doubt that anybody's going to be told exactly what's being done, because that's the last thing you need to do, is tell what you're doing to prevent from being hacked. So that wasn't neither one of those a very definitive answer, but it's the best I can do, given that these things are relatively well kept secrets. Now we're going to look at a picture here now. We've got, I love these acronyms here, LOLLY and LOLLIP. It's almost like lollipop. There's the loss of load probability and loss of load expectation are two different things. And the loss of load expectation simply says that the utilities try to design, and here's an answer in a way to your question about the grid. The utilities are trying to maintain a grid with a target of losing less than 1 day in 10 years of operation. And that's pretty reliable stuff. All right, and it's a lot more difficult to do that now, as well as as things get more complicated out there with weather-wise. And loss of load probabilities. Well, we're going to look at a picture that will show how these things relate. The ELCC is the effective load carrying capacity. And when you add new generation, your load carrying capacity is not necessarily going to equal a generation. So let's look at the picture and see what this really means. Let's say here's our target of the LOLE, loss of load expectation, in days per year. 1 day in 10 years is a tenth of a day in 1 year. Okay. And so this is what we're going to try to do. And below that is good. Okay. It means that your grid is meeting those expectations. So here's an existing generation on the blue line. And notice that as the load goes up, the chance of that generation having a problem increases until we get to, say, 10 gigawatts with this load. And then at that point, when this generation is supplying 10 gigawatts, at that point, the loss of load expectation reaches this 0.1 magic number. So as long as you're running your machinery conservatively, it is probably going to be more reliable. But if you are forced to crank out more, then you have a bigger chance of having a problem. So let's say then, let's add some new generation. That'll help solve it. Let's add 750 megawatts of new generation, okay? And by the time, though, we get up to 10, we're still okay. We're still within the target, but we, at the point of about 10.4 gigawatts, or in other words, an additional 400 megawatts, we're up at our target, and beyond that, we are not meeting our reliability expectations. So bottom line is, if you add new generation, you can't just add 400 megawatts of new generation and expect that'll solve the problem. You're probably going to have to add closer to 800 megawatts in order to meet your LOLLY requirement of 1 day in 10 years. So adding that new generation certainly improves things, but the amount you add is not equal to the amount that is useful at high load levels. Okay, so this is an interesting thing. It surprised me when I first saw it, and it took me a little while to digest it. But it does make sense now, because it simply says the harder you run something, the sooner it's probably going to give you a problem. And I guess that's true of automobiles and a whole lot of other things. Even if you do that with your body, I suppose it kind of reaches a point where it says, okay, I give up. Q&A. Hoffman's reserve margin reevaluated. Yeah, okay. We're gonna, I think, see some answer to that. So let's move, and it depends on the region. And the various entities are required to be constantly evaluating what reserve margin they need. And in fact, reserve margin, you've got different kinds of reserve. You got spinning reserves and you have non-spinning reserves. So all those things, different times of the year, you'll have different answers. We're going to look at some things. Just to note that to get a 400 megawatts increase in the ELCC, you need more than 400 megawatts of new generation. Here's a typical utility load profile. The extra dotted red line is a winter peak in the morning if you've got electric heat. Otherwise, typically you peak out somewhere around 4 o'clock in the afternoon. And about 5 o'clock, there's a dip, which is when everybody locks up their office and heads for home. And that's when there's an increase in air pollution from automobiles, but the electric load drops down fairly quickly right about then. So recognizing this load profile, this is the kind of thing that on a smaller scale is what the all the system operators have to be paying attention to, is where are we going to be tomorrow at this time when it gets 5 degrees warmer or 5 degrees cooler. How many units will we be able to shut down as a result? Okay, so here's a profile. They're looking at these things all the time. And let's look at what generators can do to help meet that profile. Base load takes a long time to ramp up. Base load, big coal, big nuclear, big anything. So, but it's also historically been the least expensive. Now, interesting, now photovoltaics is very cheap way of making electricity, but it's not very good at doing base load at night. So some of our base load generation, we're going to have to figure out some way to do that. And of course, they have already figured out how to do that, and we're almost there. Let's see, what are we doing for time? 3:23. We've got think about time. Okay. And here's partial answer to the question. Some plants are designed to be able to follow the load variations on an hour-to-hour basis. Other plants are designed, and whether the generator can meet the changing load, it usually depends on the time it takes to achieve synchronous output frequency. In other words, get up to speed. So that's why utilities are required to have some generators that are already running at full speed so that it can synchronize with the grid faster. So that's where we get the concept of spinning reserve versus non-spinning, or in other words, they simply shut the thing down during those nice balmy spring and fall days where you don't have to have that extra, where your peak load goes down a little bit. In fact, maybe even shut some down and do a little maintenance work. All right. Generating efficiency versus size. Small generators are less efficient than large generators. Let's face it. If you can get 6 kilowatt hours per gallon, and your gallon is, or your gasoline is it's $4 a gallon, that's pretty expensive electricity, isn't it? 6 kilowatt hours for $4. That's about 67 cents a kilowatt hour fuel cost alone. So, but you notice that as the generator gets bigger, your cost per gallon goes down. I mean, your cost per kilowatt hour goes down. So bigger ones. Now, here's an interesting thing for an electronic inverter. Efficiency versus power, 95% efficiency, almost all the way out to full range power. That's impressive. And these things come on, and they can come on in a matter of less than a second. So it's very interesting to then take a fossil fuel generator that is supposedly working at a certain frequency and connect it to an inverter by changing the output of the fossil generator to DC and then re-inverting it again. That way the fossil generator can run at half speed and burn a whole lot less fuel and be a whole lot more efficient at low amounts of fuel. So inverters are going to be playing a very significant role in increasing the overall efficiency and increasing the reliability of the grid. Question here. Have things changed where base load is not the most expensive as coal and nuclear seem to be high cost? This is, okay, the coal and nuclear, by the way, their operating cost is way down unless you build them. We're talking about their overall lifetime life cycle costs, those numbers you had at first. And yes, a smaller natural gas generator is relatively easy to ramp up and down. Some of these spinning reserves will, I think, from what I understand, is typically natural gas. Now, some of them are jet fuel to be really fast, but they can turn them on very quickly, like a jet engine. And within a few minutes, the thing is up to speed. So that's the turbines. So let's see, where base load is not the most expensive as coal and nuclear. Yeah, we need to, and first of all, like down here, Florida Power and Light is almost completely out of, they generate almost nothing with coal anymore. They've moved everything over to natural gas. But coal used to be one of the least expensive if you don't count other costs associated with it. And so okay, I guess we sort of covered that yeah, natural gas is mostly what's being used now for ramping. Not too unlike ramping your automobile engine up and down when you want to go faster or slower. You see buses that run on natural gas, so obviously they have to be able to ramp them up and down fairly quickly. All right, so it's interesting to look at efficiency versus power curves for inverters versus a typical rotating fossil generator. But if you combine the two, then you have an overall more efficient system, and you have to have something to run that inverter. Whether it's solar, you can even use fossil fuel and an inverter with it to make it more reliable and more efficient. So typical response to load change in milliseconds in an uninterruptible power supply in particular. That's basically what an inverter is an uninterruptible supply. What in the world is security constrained unit commitment? Well, let's find out. That means that generation is committed 24 to 48 hours in advance to all startup of large thermal units. Okay. So there's partly an answer to a previous question that people have a pretty good idea what it takes for these things to turn on and get up to speed. So they need to know what they need to do in order to buy the time necessary to get the big units running. And a lot of this based on load forecasting. And what's interesting, and I find absolutely fascinating, is that they generally can accurately forecast a load within about 2% of the anticipated peak load over a 24 to 48 hour period. They've gotten very good at that. And the weather reports, of course, more accurate weather reports help this a whole lot. Too much or too little commitment can be a problem. I think that's probably pretty obvious. Overcommitment means you're very inefficient. You got things running that aren't supplying any electricity, but undercommitment means that you could you need too much very expensive peaking equipment, the jet fuel kind of peaking equipment. You're looking at some of these fast peakers costing, my understanding again, up 40 to 50 cents a kilowatt hour, maybe even more, if you undercommit your spinning reserves. So these are the challenges that come up for these folks who run these systems. Let's see, we have another question here. What do we got? Could peaking stations provide power needed when PV and wind cannot provide what's needed? Don, I mean, the answer is yes, and it's just a matter of what kind of peaking stations are we talking about, because there are lots of ways to do peaking. And we're going to talk a little bit about some of those. We're on our way there. Okay, so you can see the problem though. And I mean, you're running a utility, and if you overcommit or undercommit, overcommit gives more reliable, undercommit means you're setting yourself up for it's lower cost as long as you are able to do it. But if you're asking for trouble with an unexpected, what if a large generator goes down for some reason unexpectedly? And if you're undercommitted, then you have a pretty serious problem, and you're probably going to have brownouts or blackouts somewhere. Okay. Now, the balancing authority generally sets a schedule once a day. But it depends on the balancing authority. Some establish their schedules more frequently than others. So what about reserves? There are contingency reserves in case of sudden generation failure or a transmission failure, and you have to have those. They're non-event-based reserves, and they're used to manage short-term fluctuations in demand as well as load following reserves. Okay, now here's the interesting thing. Again, if you got a flywheel up to speed, it means that thing, and if it's really well balanced with nice magnetic bearings and all, it can be spinning at exactly the speed it needs to spin at. And in the event that there's the slightest fluctuation in the frequency of the incoming power at the site of that flywheel can be told to, you come on right now and you level that thing out. And they're good for on small scale, up to about 5 minutes of fluctuations, and on a larger scale, probably a little more than that. So that's one of the, in other words, you don't necessarily need a fossil fuel kind of a thing. A flywheel is a kind of a storage thing that can be used to meet the need for reserves. Anything that's there for frequency controlling regulation, they have to be spinning right away. It's simply not time to get them up to speed if it's a rotating reserve. The other thing that will undoubtedly happen with flywheels, maybe it's happened and I haven't seen it, is they will be dumping their output into big inverters as well. Then as they slow down, they can still, it's a little less efficient that way because you have to convert to DC and then back to AC, but you can run them a little bit longer and still maintain very constant frequency. When you lose generation, your system frequency takes a big jump down. All right, here's an example. Big loss of generation, one big one goes out and the frequency drops down, say down to 59.9 from 60. And what happens on all of the fossil machines, the rest of them, they have a governor that says, whenever you've got a governor that maintains your speed, and as your torque requirement increases, as your power requirement increases, your torque requirement increases, and therefore your fuel increases. And that's what your governor is all about, is to maintain the speed. It looks like stepping on the gas to maintain the speed while you're going up a hill. And then you've got your AGC response that happens about 3 or 5 minutes later with your generator. and you dump another one in from your spinning reserves, and you get yourself back up to the necessary frequency. So that's one way to do it. And this is the kind of curve you're looking at, and this is a trigger, is the instrumentation is looking at that frequency, and if it sees a big spike like that, everything else on the system knows exactly what it needs to do, just like a hockey team when the puck goes down to the other end of the ice. So AGC is system automatic generation control, which means turning on that generator when you need it. Okay, and of course the generators themselves are almost a form of flywheels because they got these big, heavy, solid steel cores that have a lot of rotational inertia. So what's the observation? NREL says new transmission could address the general increase in grid congestion and support the creation of broader markets for electricity, as well as support the future integration of renewable resources. All right, expect new transmission, bottom line. And like when PV is peaking in the West, at that time, around 12 or 1 o'clock, we remember that demand curve, 4 o'clock in the afternoon is when it generally peaks. Well, 3 hours later, out east, that electricity from the west that travels at almost the speed of light can zip its way on east. If it's at super high voltage DC with minimal losses, and it makes a fairly good argument for studying the economics of increasing west to east transmission capacity and interconnection. And I'm sure that studies like that are happening right now because there's a lot of opportunity for solar generation out west. There's quite a market for electricity out east. So one possibility here. What about transmission? How expensive is it? Well, here's another picture for you. And again, we're not going to go into gory detail on these, but it's a comparison of various transmission forms. And here we're saying we're going to transmit 6,000 megawatts at 75% utilization. What does it take? So it depends on the distance, and we've got 7 different types of generation. We've got AC generation at 345 kV and 500 kV with either 2, 4, 8 circuits. Okay, and then we're looking at DC generation. And it's very interesting. If you've not seen a DC transmission line, there are not a whole lot of them around. There's one from Oregon to California. There's one from North Dakota into Minnesota, goes along the interstate and along Highway 55. Used to live there and used to drive along that on the way from Minneapolis to Glenwood. And it's very interesting to see just 2 big wires and a ground wire along the top rather than 3 wires in a typical 3-phase AC circuit. But look at the cost. The least expensive for 1,000 miles is an 800,000 volt high voltage DC. Whereas if you want to do that with 345,000 volts AC with 8 circuits, that's the big, tall blue one. So bottom line is, I think we're going to see more DC transmission lines coming up for some longer distance, because even at 250 miles, the cost per megawatt hour on a DC 800 kilovolt DC transmission line is right down in there and running. So probably going to see more DC transmission. I remember my brother used to live out in Glenwood, Minnesota, and he liked to walk out to that DC transmission line and hold a 4-foot fluorescent tube in the air, and at night it would glow. Fantastic electric field coming off that thing. Anyway, and they used to have all kinds of stories about, gee, the pigs aren't growing bigger, so on and so forth. But I think a lot of those myths have been dispelled at this point. Anyway, somewhere between 300 and 600 miles is the breakdown point, and it's highly likely that anything more than 300 miles will probably end up being a DC transmission rather than AC transmission. Okay, so just I almost want to ask everybody to raise their hand and see if, just for the heck of it, I'm going to drop down my participant list, and if I can get it to do that. Nope, it doesn't drop down. I thought maybe I could get people to raise their hand if they knew about that before. I'm hoping you learned something new today. Maybe more than one thing. That would be even better. Okay, here's your footprints. That 6 single circuit, in other words, 6 towers, 900 foot right away it takes, and they're 90 feet tall. If you put double circuits, you know, 1 circuit on each side of the tower, then we still have 6 circuits, but it only takes 3 towers. They're now 125 feet tall, but your right of way is only half as much. Now let's take a look at that 800 kilovolt DC down there in the lower right-hand corner. 270 foot right of way, smallest of all, 145 feet tall. It's pretty high, but the big 765 kilovolt AC lines are 135 feet high, and 6,000 megawatts capacity takes 600 foot right away, and we're talking 6,000, or sorry, my 5,000 megawatt capacity here with this big 800 kV DC. I don't expect too many people going to climb those poles, but we're probably going to see some of them. This is the line that happened to be in Newfoundland 2017. I had a chance to take a picture of it. I thought, gee whiz, a very nice DC line. Wonder where it came from and wonder where it's going. Well, it comes from a hydropower in Labrador. It goes underwater for a ways up there near the boundary between Labrador and Newfoundland. Actually, it's Newfoundland. Now, Labrador is an entity now, and it goes all the way down St. John's, just short of St. John's, 1,100 kilometers total, 400 in Labrador, 700 in Newfoundland. Pretty nice transmission line, both overhead and underwater. It's 900 megawatts, high voltage DC. At 350 kV, not even one of those huge ones, just a kind of a small one in a way. But then again, Newfoundland's power demands are, there's just not as many people in Newfoundland as there are in New York City. So they don't need quite as much power. But this is what it looks like. It's interesting to watch it, look at it side by side. You notice on the left there is your typical 3-phase AC transmission line. That's the history. Then you see this nice big high line here in the foreground that is only carrying 2 wires, one on the right, one on the left. Big DC transmission line. Towers are relatively distant space. And that maintenance road will probably stay, but most of the rest of the forest and wildlife, not a whole lot of disturbance to the moose and the bears in the region. So we're probably going to be seeing more of those other places as well. The Chinese are building them like there's no tomorrow. Just a list of them here. And of course, the bigger you build them, you have bigger decline in unit cost. But if it breaks, if you lose it, then you got a real problem. So it's an interesting coin toss on figuring it out. Another question, let's see what we got. Moving power to destination seems to be more necessary for wind generation. Oh yeah, for sure. As we mentioned earlier, wind is not viable everywhere. West Texas got some nice wind. Buffalo Ridge in Minnesota has some nice wind. Some of the past between some of the mountains in California, some nice wind. A lot of nice offshore wind in various places down in Central America and so forth. But So yeah, the wind is generally, the big towers are generally not in the high population areas. Whereas you can put all solar you want in a high population area, at least certainly in the suburbs on rooftops. I maybe mentioned earlier, the company I work for, we've designed about 3,000 systems just in the last year and a half for rooftops. So it's a resource. What else are you gonna do with your roof? I mean, you put solar on it, it shades it from the sun. It doesn't dry out as fast. It holds it down better. You put a 4-inch lag screw in there into the truss, that's gonna hold your roof down pretty well. So that is one major advantage photovoltaics has over wind. It does take more transmission lines, and if you factor the cost of them into the cost of the wind, it does tend to add to your cost per kilowatt hour. So yes, thank you for John for observing that. And Jennifer, Hurricane Ida in New Orleans transmission tower, prime example of lost potential. Yeah, entire city wiped out of power after the damage to the main towers crossing the Mississippi River. So yeah, again, the dilemma that we have is building these transmission and building them sufficiently securely and trying to anticipate everything that might go wrong and not necessarily guessing at all the answers right. So what do you do? It's not a simple answer, is it, Jennifer? Not at all. I appreciate your comments. Okay, I'm just clicking things here so I'll notice any new comments. So there's risk and there's advantage when you build big power. And you just kind of need to know, of course, that's certainly Japanese discovered that with Fukushima. They had it all designed perfectly earthquake proof, except they forgot about the tsunami, and that came in and wiped them out. The earthquake had survived, but it did not survive the tsunami because they did not plan for both catastrophic events simultaneously. So, wow, what a job for the planners. So, what are the technical challenges here? This is some, first of all, dispatchable means it's predictably available for planning ahead. Dispatchable energy. Press a button and you got it, okay? Some are dispatchable. Hydro is, geothermal is. Concentrated thermal solar is dispatchable if you have thermal storage, because you heat salt or whatever and you store hot stuff underground with concentrated solar power towers out there in Bartow, California, for example. If you have liquid sodium at 800 degrees and then run a conventional steam generator at night with that, then you have dispatchable power. And certain bioenergy is pretty dispatchable. So there are, it's not that all renewables are unpredictable. Geothermal, a little limited in where you have it, but Iceland pretty much lives on geothermal. They've got these huge geothermal generators about 50 miles east of Reykjavik, and a huge pipe bringing all that nice warm water down into town. Some of the stuff out there up around Lake Tahoe. There are in Alaska, of course, that's lots of geothermal. So there are sort of dispatchable stuff. And what else? Wind and PV, no, not completely dispatchable at all. But you know what? They are partially, and there's a reason for that. If you, I mean, the variability and uncertainty are real challenges for wind and solar. Fortunately for solar, you know very well that it's going to get dark at night, so that you can deal with in a separate way. The clouds coming over, that's another issue, and that may be for a whole day of cloudiness, or maybe a few big cumulus clouds clouding the sun for a couple of minutes. And if you have a 100 megawatt solar farm, it's going to drop the output probably by 50% if a cloud comes over. So you need to know, have a way of dealing with that. Okay. More is known about wind uncertainty because they've done more studies. I've tried some simulations myself about PV uncertainty, and it seems that that goes pretty much the same direction about wind, but let's look at some wind pictures. They have less variation if they're aggregated over a large footprint. That makes kind of logical sense, but exactly how much, you'd have to do some measurements on that. Kind of hard to do a simulation exactly. You need to do a little measuring. PV output, yeah, you know, the cloud can come across the sun pretty quickly, but the wind doesn't just stop just like that and then start up again. It may be gusty, but people tend not to want to build windmills where there's going to be gusty wind. So wind tends to ramp more than PV. So wind is a little easier to deal with. PV installed at the distribution level can challenge the management of distribution voltages. You know, that's an observation. It can, we discussed that earlier. Concentrated solar power with thermal storage can ride through solar variations up to 6 hours, depending on how much of this hot melted sodium you decide you want to save. So that's certainly a big help if that hot sodium is available with a spinning generator or something to help through cloudy periods out there in the desert. And solar and wind also can ride through variations, and it all depends on the storage levels. Institutional challenges. How can we do it? Just demonstrating a principle is only a beginning, because there are institutional challenges saying, we don't know for sure, we want to let you do that. And there's a lot of inertia. Talk about inertia that's needed to keep things running. There's also a lot of inertia that stops things from moving the way they ought to. But that's being dealt with. And money is generally the moving factor there. Anyway, fundamental principles have emerged from integration work on wind. We're going to see a picture here in a minute. Yeah, the permitting of getting a system permitted. Any PV installer will tell you that their biggest nightmare is trying to get a set of plans approved by the plans examiner and the permitting office. Maybe not. There are some places where it's harder than others. Certainly can vouch for that. Okay, here's a picture. Time for a picture. The load is in green. The net load, the wind output, is in red. So if you subtract the red, in other words, you use all of the wind to meet as much of the green load as possible. What's left over is a net load that has to be met by something else, the blue. And the key here is that, notice the slopes here. Notice at about 50 hours where the blue, the net load, the ramping up is a whole lot faster in the blue because the wind slowed down in that time period than it is in the green, which it would have been without the wind power. So that's something that has to be dealt with, but at least it's a whole lot easier to deal with something when you know about it. And this is something that's been observed. And notice the time frame here. We're looking at 160 hours here. And so you're looking at a couple, the time not in minutes, but in hours of getting things ramped in to make sure you can make that sharper blue ramp for the net load. because that net load has to be supplied by other generation. And of course, the other thing is, what if the wind power exceeds the load? Then the blue goes negative, or presumably then what happens is that extra electricity gets sold to another area that needs it. So anyway, questions there. Recent analyses, 30% wind generation or large footprint has been analyzed. And in other words, let's look at the pictures here. And here's what they look like. In 2006, they did some studies. And notice the wind power, notice the horizontal scale. Okay, and the top left one, you're doing 3,000 megawatts of wind power. And the bottom left, you're doing 30,000 megawatts of wind power. Notice that the line is straighter. In other words, the deviation from the expected power from the total system is much less over the full range of power needed, all the way up from 0 to close to 30,000, as in the one above it. You notice you're almost 20 plus or minus 30% deviation for the smaller aggregate of wind machines, and the deviation is only about plus or minus 15% for the larger aggregate. Similar study in Colorado, similar thing, 1,000 megawatts versus 7,000 or 70,000 megawatts, and significant increase in predictability of, or for significant reduction in variability of the anticipated power from the system, because when one windmill is slowing down, another one's ramping up, and the two kind of cancel each other out and make it kind of constant. So that's what we're looking at here. And there's no reason to believe this isn't going to be any different for solar, except that rather than plotting it by the hour, you need to plot it almost by the minute intervals. And that gets a little more complicated. Tracking is an option for solar. What we see here is a fixed, the one on the left is just looking south. The one on the right is rotating from southeast to northwest over a horizontal axis there. This is in the afternoon, it's looking south, more to the northwest. But in the morning, that thing's tilted looking to the southeast. And the local university here has some data on that. And this was installed for a while ago, and nobody knows where the data is anymore. So I never did get any data, but there's reason to believe that tracking, if you want to increase your stability a little bit, and if you want to increase your peak time output a little bit, tracking can help. On the other hand, tracking takes a bigger footprint because you don't want one table of modules to shade another one, so the separation has to be bigger than if you have long rows of fixed tilt. So it's all a matter of what you want to build. But I thought you might be interested. It's an observation that not everybody's necessarily thought about. And again, we're just trying to create some thought here. And I didn't promise that you would be able to go out and design one of these things or any of the other stuff, but at least you'll know about it. So what's the financial impact of improved scheduling? If it's not worth, if improved scheduling doesn't save money, then why bother? Well, General Electric studied in 2005, it showed that you can save money if you have better wind forecasting. And again, it's a no-brainer. If you had perfect wind forecasting, you could save a whole lot of money. So a little work on improving forecasting, it's happening right now as we speak. Of course it is. Because there's a lot of folks building windmills out there, wind machines, sorry. I didn't mean to call it a windmill. But it saves money by being able to forecast properly, because you can predict when you're going to be needing extra electricity. It saves you money. And here's another interesting dilemma. Let's, what do we got for time here? Oh, it's 4 o'clock. My goodness, I got to go fast. I'm sorry. I'm gonna, this is something you can read. It's pretty obvious stuff. Dilemma is when you've got solar or wind power, everything has capital, operating costs, and fuel costs, except for solar and wind, they have capital and operating costs, including maintenance costs, but no fuel. So therefore, if you don't have a fuel cost, you want to make as much electricity as possible with it because there's no fuel cost. And so you get more for your money the more you make. On the other hand, the only way you can pay for a generating facility that requires fuel is to burn the stuff and run it. And the longer you run the facility at the higher capacity, the faster it pays for itself. So here you got these two conflicting things. So what fun to try to figure out how to mix these. Well, the economics is going to show that it is too bad that there's other things out there other than just money. There's this air we breathe and a lot of other things that are important. So flexible loads, electric vehicle charging or discharging, connected up. You can easily tell an electric vehicle, hold off, don't charge now, we need the electricity for something else. Aluminum production, thermal storage, the smart grid. Half of the ERCOT load is responsive. And that's the maximum that's allowed, okay? Being flexible. Demand management for air conditioning, water heating, pool pumps, all kinds of stuff. So there are lots of ways of making loads more flexible. We don't just have to do it from the generation end. There is a lot of opportunity on the loads as well. The concentrating solar power with storage is flexible generation. Small thermal with inverters to increase partial load efficiency. Another flexible generation. You know, smaller generators, smaller fossil generators, but inverters. Diesel and gas turbines, they can start quickly and they can ramp quickly. Hydropower from reservoirs, half an hour turnaround time to between pumping uphill and pumping downhill. So they're letting it run back downhill. So another pretty good flexible generation opportunity. It's not solar, but hydropower. And if you make that, hydropower is now becoming very popular for storing excess solar energy during the day rather than excess nuclear at night. So there's the environmental constraints, but if the hydropower is already there, you might as well use it effectively. Energy storage, pump storage hydro is the biggest one out there. Compressed air is the next biggest. Battery technology is rapidly. We have a separate, a totally separate 2-hour webinar on storage, by the way. So we're just talking about what exists now. If you want more details on storage, you might want to look up in the PDH catalog and see when they're going to offer that. Large capacitor storage, not really commercially viable right now, but one thing that is definitely commercially viable are the flywheels. I'm trying to go kind of quickly. We're almost at the end here now. What will all this do to the grid? Well, here's what we've got today. Mostly just generate it, distribute it, and use it. But as we move forward, it's going to look more like this. You don't just generate it. You notice the line, the arrow only comes out of the generator. You do not store anything in the generator. But if you go to the neighborhood, you've got some people with small PV systems, no storage. You got some people with PV with storage, and we're going to find there will be some people who have storage and no PV. But in any case, when you got storage, that can level loads. And you notice the directions of the arrows. Energy flows in both directions. PV, energy only flows out of it. Storage, energy flows in and out. get on top of a big box store, you got a bigger load. You can have a small PV system, small storage, small meaning 100 kW, 200 kW, depending on the roof. Smaller storage, neighborhood of maybe a couple hundred kilowatt hours. Get to a substation, add some renewables and some storage. Get somewhere along transmission where your 100 and 200 megawatt systems are, the utility size, big renewables. Just need to add some big storage there. And and it's not all going to be lithium batteries. There's a lot of other interesting things out there, including lithium batteries, where there's a 100 megawatt storage system out in South Australia that was built in less than 100 days. So interesting stuff. Anyway, this is what's happening. And let's just think here for a minute. What's the ideal energy source? Follows the load, operates efficiently, is economical, not subject to fluctuations, fuel price, doesn't pollute, it lasts forever, and it can be developed, installed, and used by hostile countries without causing a threat to other people. We don't care how much photovoltaics the Russians are installing, for goodness sake. The Chinese are way ahead of us in installing wind and solar. Nobody's fussed about that. It gives them an economic advantage, maybe. We maybe need to be thinking about that. But anyway, from a prediction standpoint, I think you see what we're saying here. We're probably heading in the right direction. I think they were right in 2012. And that brings it to an end. Windmills along the road. That windmill down there and that solar, the lower left-hand corner and the bottom one, those are in Yellowknife, Canadian Northwest Territories. So don't say you can't use solar up in the far north. They love it. And that other big solar farm is up in North Branch, Minnesota. It's 100 megawatt, I think, that Xcel Energy built there. So thank you for being here. Sorry, we ran over by 7 minutes. That's probably because I was counting how many people raised their hand that were still awake. But anyway, if there are any other questions, I'm going to stay online for a little while. I know our host is going to want to shut down and go to dinner. But thank you for being with us. Hope this will help take care of a couple of your hours of continue ed. I had to just finish up my 18 hours on Sunday. Hopefully this will help you finish yours as well. And have a wonderful week, everybody. Oh, there's a lot of other fantastic, interesting storage other than flywheels out there as well. Believe me. If you're interested in energy storage, sign up for the energy storage webinar. We talk about lots of different storage mechanisms. Okay, thanks to all of you for being there. Much appreciated. And now I get to go back to reviewing solar plans. And Mr. Host, thank you for making this presentation possible. Oh, and if you go to the chat box, that will give you instructions for where to go from here as far as taking a quiz on this. And it helps probably to download the slides just to take the quiz, and how to get your certificate. That is the administrative information that you're looking for is in the chat box. Okay, Mr. Host, I'm going to stop sharing my screen now. And I'm going to find that close button. That leave button, that's the one I'm going to click.